Hello everyone. With a very good session on data mesh, which gives us a strategy to manage the operational side of data, we are now diving into some of the operational or transactional side of data. So let's look at what are the large scale enterprise challenges in building data architectures, especially when dealing with scale, right? Yeah. So with large scale, the enterprises need to deal with a completely different level of complexity that entails the scale. We will look at what are those characteristics of large scale enterprises which entail this complexity, and what are the as-is architectures that we typically see in the large scale enterprises, what are the challenges that they face with their as-is systems, and what are the drivers for them to change or modernize, and is the change also easy while we say that they are facing some challenges with this scale. So let's look at that. So at Thoughtworks, we worked with quite a few large scale enterprises across different domains, including retail, finance, healthcare, insurance, aviation, as well as payments. Across all these domains, what was common was that they were dealing with a lot of data. And when we say a lot of data, their usual operational systems have to deal with the data at this scale, and in doing that, they also need to ensure some bit of transactions. And when we say transactions, we are talking about mutations on data, right? And ensuring that the data is getting saved or getting ingested, getting processed. And given that all of these domains are related to public services, it also is connected in some or the other way with our day-to-day lives. Many of these services we end up using daily or also frequently, right? And while doing that, they need to ensure that as digitization and digital transformations improve, there is a lot of increase in the user base also. So they need to be able to cater to millions of users in order to scale their businesses. How do they really do that, right? Let's take a look at it. Let's consider let's consider one example wherein we talk about a large-scale retail store. Now, most of these businesses are quite old, right? And they are also present across multiple countries. And not just that they have some brick and mortar stores, which are also in thousands, but they also have some e-commerce platforms whereby even entrepreneurs can open shops for themselves online and start selling the material that they want to. So with this, the scale suddenly grows as you think about an e-commerce platform also for in retail. Now, when we say when the scale grows, where does the scale come from? Where does the scale for this volume of data come from, right? So many users and others. So the nature of businesses itself has changed with the changing technology landscape. Right? We can see that a retail store not only has a brick and mortar store and the data getting generated out of that, but there is a whole lot of spectrum through which the data flows into these systems. And it starts with online clients. Everyone here would be ordering something or the other every day. So those devices also generate some data, and those devices contribute to a lot of the data share. Earlier, if you think about 20 years back, the data that was getting generated and stored, it was primarily going to be stored in one location. But today that is not the case. It's a whole spectrum from the edge devices to the actual data centers or actual systems where the businesses are working. Now, supply chain is another thing. You might be ordering products that are getting shipped way from the different corner of the world. So all of these supply chain systems also contribute to a lot of data here. Warehouses are getting huge, right? And they're also getting a lot of automation there. So warehouses contribute to much larger share of data here. In fact, some of the warehouses where the automation and IoT kind of technologies have been applied, their larger share of data comes from warehouses rather than stores. Those are also the challenges that they face. And yes, of course, the real part of the business is the stores, where again, as I said, not just the checkout counters, but also there are devices that are being used, or IoT devices being used to ensure that on the aisles or on the racks, the products themselves, how much quantity of products are actually available, and when do we want to really refresh them. So how does all of this work, right? We talked about a whole spectrum of devices and whole spectrum of systems that are being put to use in order to serve the orders that you and me are placing every day. What are the kind of systems that actually make this work? A larger share of this data, heavy lifting, is being done by the mainframe systems. Take any of these domains, financial domains, retail domain, or healthcare domain. Mainframes are still out there while we talk about all other technologies. And while we think about mainframes as a plain old box which kind of does some kind of processing, mainframes have also evolved. So if you look at today's architecture for mainframes, they are capable of having around 2000 processors on one box and 40 terabytes of memory in it, right? So there are powerful systems out there which continue to power some of the public services that you and me use every day. While larger share is taken by mainframe, it doesn't mean it is all about that when we say large enterprises. They have also over time offloaded or modernized some of their systems onto some of the on-prem data centers, or those are the systems that do not need a lot of scale, right? And usually when we talk about writing applications or modernizing applications, it is about ensuring that when we bring them out of mainframe and when we make them ready for cloud, they could be deployed either on-prem or a public cloud. So basically the idea is most of these enterprises would like to have an option to go multi-cloud. So on-prem systems are also kind of expected to be compatible with the cloud ecosystem. Yeah. Now, how does the architecture for these systems look like? We talked about the scale, but does the architecture really support scalability here onwards, right? And there are different varieties of architectures that we can see here. On the mainframe side, you can see monolith architectures, which are huge systems built over decades, multiple programs or multiple features being implemented in the same system, using the same old or using the same major database. And while you look at the modernized world, there is an effort in terms of splitting that system into multiple systems to reduce that complexity. While we say we are moving away from the monolith, but we are just separating here only the processing part of systems. The data is actually still there in the mainframes, and in the name of modernization, the complexity of splitting the data is actually taking backstage, and we are creating layers called data fabrics or some virtualization layers which will make the modernized systems talk to the data on the mainframe side. So the data still remains monolith. And on top of it, when the microservices wave came in, we tried to do some data separation, but again not around the core data. Most of the data that kind of gets separated or modernized is around the ancillary systems, which are easy to separate out, but the core of the domain, be it retail, be it financial systems, any domain, it remains still on the same mainframe because the core has to support all the load that comes in. So essentially we end up in an architecture wherein there are all sorts of, or we end up in a state where there are all sorts of architectures out there. We have single monolith application also, we have highly coupled systems also, and we are not talking about one or two systems being coupled here, but we are talking about whole dozens of systems being coupled here, which are running this whole this whole business. And yes, there is an effort in terms of separating out or creating microservices out of this, but those microservices themselves, if we zoom in a little bit there, even there, the operational data is not really well thought about. There is no coherent data strategy across these operational or transactional systems, right? And then when we talk about data, right, as is data, what is the size and shape of this data? We talked about dozens of systems here, right? Many systems, even an individual system has to handle terabytes of data. We talked about an enterprise data scale when we talked about gigabytes of data or petabytes of data being generated per hour. But there are even systems which need to tackle terabytes of data in that one system. Imagine a microservice which is handling that much of data. How will your query run? Like, what will be the performance of your query there, right? And when we say this is the size of data, when we talk about the shape of this data, When I say shape, how many tables do you have, right? If we imagine it as as a relational model, and how many columns do we see there? Practically in a large scale, we have seen tables of the order of 500, 600 tables, each table having columns of the order of 800 or even 1000 columns there. Why is it this case? Because the business itself is very old. The systems were built over decades. And when probably they started with a small data model, but over decades as the business grew and the data model also evolved, they kept on adding to the same monolithic data model, which kind of now resulted into this. And while they're supporting millions of customers here, which are the end users of the system, but essentially because the business model is a platform model or a business to business kind of model, here there are hundreds of tenants, which means actual entrepreneurs who want to sell their products over this platform, which means you also need to ensure that there is proper multi-tenancy design which is considered in your data architecture to ensure that one tenant doesn't get affected because of the other. Maybe one tenant had got a lot of orders during peak time, the other tenant should not get affected because of that. All of that we need to ensure. We need to also ensure the security for data for each of those tenants, compliance related needs, everything. With mainframe that gets a little difficult. Now, we talked about slightly the legacy challenges, but what are the business drivers? All of these that we talked about were technical issues of maintaining that system. What are the business drivers? If we look at businesses today, even maintaining this old system is getting very difficult because of the fact that either the cost of the hardware or software might be rising, the license costs. Even the license periods also might get to an end of license stage, end of support contract stage. Skill set is another major issue, right? The way the technology landscape is changing, hard to get people who can work on mainframes. There is also increasing cost of changes, which means the same change if you want to implement in a modernized stack versus the change that feature if you want to implement in the mainframe stack. There is also higher cost of opportunity or even implementation cost. Businesses would definitely like to reduce on these costs, and that is possible also. With all of these complexity, the scope and estimates are never correct. So it has direct impact on the cost because either the people are not available or the technology doesn't support it. So either the estimations go wrong and the cost increases. There is also incompatibility between what the current business process is and what might be required in order to modernize it when you federate the systems. We will come to that, we will look at that in details. And this also leads to some kind of off-system workarounds where people have to do manual changes or manual workarounds in the existing business processes. Now, if we look at, apart from business drivers, what are the other drivers? Business definitely wants to have some competitive advantage in the market, right? Maybe there is a competitor out there who's aggressive and he started using IoT devices and being able to respond to the customers' preferences or even track the customers' preferences better, right? So it could be either a disruption in the technology or the competition in the market. All of these factors would force the large-scale enterprises to think in terms of how do we modernize all of these systems without affecting the current scale, and not just affecting the current scale, but also being able to ensure that whatever investment do they make for this, these investments are not small. Legacy modernization has huge investments, and even the success rate of legacy modernization is not very good. So how do they ensure that when they invest so much, they are able to handle the growing scale for another, let's say 5 years down the line, 10 years down the line? Now, apart from the business mandates, right? Can we take the existing system as is and put it to just change the technology, but keep the entire process and the data as it is? Is that possible? Probably not. We'll have to give it a second thought. We'll have to think about what is really the best way of modernizing this particular system. Why so? We've seen that there is a lot of coupling that we see usually in the legacy. And this coupling essentially comes from the fact that as new systems got added over decades, they started using the same data. Now, because of that, what happens is two completely unrelated systems may be affected because of one single change being done somewhere, and multiple systems get affected. And here, there is also a possibility that the database becomes a single point of failure. Maybe the load on your online ordering system got so high that in the new world, mainframe was able to handle that, but in your new world, maybe the databases or the technologies that are out there, they cannot compete with the mainframe scale. And because of that, the database went down and all other services eventually cannot respond to anybody. Now, there is also a possibility that all the systems start scaling together because there is, let's say, a festival and there is huge demand and you are seeing a lot of traffic across all the services. The database cannot handle it again. And the other part would be that even if, let's say, the database is able to handle it, is not completely down, but it cannot support so many connections. You might also have to add new features, new services. It might not be possible because of the sheer limitation of the technology. So what is the solution? We cannot take the as-is system and modernize it just like that. So we need to split it. When we say we need to split it, we need to break that monolith. Right? Usually breaking the monolith is perceived as a complexity for breaking the processes or breaking the functional part of it, right? Processing part of it. But a huge challenge also lies in breaking the data, monolithic data. Usually those of you who have seen the microservices, who have seen the mainframe world might have heard about this term called system of records. That is what it is called because it's a huge data and it acts as a source of truth for multiple or most of the data in the enterprise. Now, how do you break that system of records into and create sources of truth? Not just one, but multiple sources of truth, right? What logic do you apply here? Because you know everybody is using everything. We'll come to that. But essentially, by doing or by breaking this, why do we really break it, right? We saw that we cannot take the as-is system and modernize it just like that. But then if we have to break it, why are we really breaking it? What is it that we are getting out of breaking it? One, as you break, you can scale different parts independently. And the second thing is, when you are breaking it, you are also allowing different parts to change independently, not just scale independently, right? Maybe one system needs to undergo change quite often, the other system doesn't need to undergo that change. Maybe one system needs to use a different technology. Here it was all one technology, right? We saw that operational and analytical data was same, operational and analytical systems were also together, with the same, implemented with the same technology. But here it is possible that you feel that, okay, I don't need a SQL database here, I would like to use a NoSQL database from the cloud and manage my latencies better or manage my scale better. So that is possible if you break it. So different features, different systems will have different characteristics and you will have that leeway in order to design your systems accordingly. Not just that, you will also ensure that you are addressing the business challenge, that the business can now respond to new features, new changes, disruptions in the market easily because only that part needs to change. It has now been decoupled with the other parts. But the other advantage that you have here is you are also making, by translating or transforming it into a new technology, you are also enabling a change that allows you to go cloud native. Because most of the technologies that you will select will be cloud native. So we looked at what are the advantages of splitting. It's also called federation. But how do we really do that federation? And what are the challenges in doing that? First challenge, as it is very, very obvious, that every system is using all the data out there. How do you split it? Take an example, a product. Okay? Right from your inventory to your catalog service, to your procurement service, or even to your online ordering system. Every system is using it. Even your analytics is using it. How do you break that product? But remember, although we have a common database or a common entity being shared between different systems, we also know that that entity is huge. As I said, each table there had like hundreds of columns, right? Hundreds of attributes. Not all the attributes will be required by every system. So we need to apply some boundaries. We need to figure out what are those boundaries that each system is operating within, right? Now there is a catch. If you say these are the 20 attributes of product that I want to separate out in a product table, and I would like to assign that product table to, let's say, an inventory system. And to you logically it looks really correct that okay, the product categories and everything, it should be with the system and how many units you have and all of that. But if you look at the top diagram here, what happens here is the moment you try to separate out, let's say, these 50 attributes, you suddenly realize that okay, there are 20 other systems that are using it. Because we are talking about a very large scale enterprise where there are multiple systems, maybe some other systems are using that data, and when we say using, we need to understand whether it is just a read-only access or is it also modifying it. Particularly if they are modifying it, then that becomes even more difficult because it's a decade-old system. You never know who's modifying it, right? You will figure that out only post facto, like after 3 months down the line, 4 months down the line, if nobody knows it. A lot of times it so happens that with modernization, these are the challenges that nobody knows what is out there, and you only uncover as people go do the reverse engineering of the existing stuff. So here it is important to not just look at one service, the need for one service and then separate it out. It is also important to look at the holistic context of what each system is doing. How are two different systems overlapping with each other? That systemic view or that domain view has to be there. Without that, it becomes difficult and complexity increases basically. Okay. So for that, when we said we need to understand what each system is doing and have a slightly abstract or domain view, functional view of system, we need to understand what are the domain boundaries. If we say inventory, if we say procurement, what are the attributes or what are the things that inventory is doing? Have a process map. Figure out what are the processes that happen in this inventory domain, and then what are the data requirements for that inventory domain. That clarity has to come in, and no transformation works without business and IT and functional SMEs working together, right? Typically this is the challenge. If IT people or if there are technical experts sitting in the corner and figuring out how to break a database into or how to separate the different domains, it is not possible. Neither domains nor databases. It has to be a collaboration between different organizational units, and within each unit, the business and technology expertise has to come together and decide about that. Now, once we know what are our domain boundaries and what are our data requirements for each of those boundaries, automatically we will also know that, okay, these are the, let's say for example, who owns what? Right? That is another question. So once you know the boundaries and once you know that the data requirements, you can easily say, okay, maybe product is being used across 20 different systems, but I would like to ensure that product is owned by, let's say, the inventory system, because that is the system that is changing it very often. Catalog system is only changing it when the product comes in or gets decommissioned, which happens only once or twice in the lifetime of the product. But the inventory is getting updated every day, so I would like to have it as part of inventory. There are trade-offs there, but just as an example, the domain ownership itself can only be decided after we figure out what are the different domains, what are the different functions that those domains are trying to address. Now, you might have done even ownerships, but there are now overlaps, right? Now, how do you address those overlaps? First, we need to look at what are the dependencies between the domains. Do those dependencies even make sense? Those dependencies might have been created over a period of time, but do those dependencies make sense today? Is there a possibility that you shift the dependencies? Or you try to ensure that when we say ownership, actually we would like to have one domain own that particular data and ensure that the changes of the data that need to happen to that data happen only within the bounds of that domain. That's what we call as ownership or source of truth, right? There should only be one source of truth, so other systems should not change that particular data. And if we keep that as the definition of ownership, then automatically you will have to rethink your business process boundaries. Maybe 20 different systems are updating product, but you need to move that logic of updating product to the product system, to the inventory system if you have decided that. And there are ways to figure out how some of the unrelated functionalities also can be brought back to another domain. You could have something like a delegates pattern also. There are different ways. In the interest of time and in the interest of covering other challenges, we will go ahead. But this is a very, very important step in terms of ensuring that your legacy modernization succeeds, because you can neither break processes or systems apart, nor can you break your data apart unless your domain boundaries and domain definitions are not very clear and they are not really segregated based on their purposes. Yeah, one more thing is we need to identify, it's not just about splitting. We have talked too much about how to split, but it's not just about splitting. It is also important to understand what are the two pieces of data that need to reside together. And these are called the drivers for splitting or drivers for combining this data, right? Maybe you are doing some asset transactions. Whenever your product inventory is changing, your order or your payment is happening, the inventory should only get changed after that. It shouldn't happen otherwise. So these are the kind of examples where we are trying to do atomic operations together, and it makes sense to put them together, combine that data. And there are different ways, there are different patterns that can apply there. Again, I think each of these challenges that we are talking about are they are in itself a topic for a larger discussion, but in the interest of time, we'll go ahead quickly. In terms of, yeah, so we talked about federating, we talked about splitting both the processing layer as well as the storage layer. But as I said, many a times it may not be possible that you combine both the inventory and payments together, but still you have to update them whenever an order happens, and the order is your business actually. The more you get orders for retail, the more your business grows. So which means that this is your day-to-day operation where you are changing both, but they cannot sit in the same domain. They have to sit in the different domain. So how do you integrate? Right? Do you use synchronous mechanisms for integrating, or do you use asynchronous mechanisms for it? And how do you decide that? You would decide that based on what is the acceptable latency for you, right? What is the tolerance for failures? The moment you split, if there are failures, there is a chance of inconsistency. And in order to avoid the inconsistency, you might have to do some kind of error, some kind of compensations or error handling. How do you ensure that it happens at a level wherein the consistency and the business semantics are not compromised? Sometimes you may have to let it go off. So ultimately it is a trade-off between what exactly do we want. Do we want the simplicity for error handling, or do we want to ensure that the latency itself is not very high? So those kind of trade-offs can be applied to decide case by case basis what integration mechanisms should be applied between when integrating two different systems. Yeah. And the popular topic of distributed transactions. The moment we say we are going to split a monolith into multiple services, again those services need to collaborate, they need to talk to each other, and sometimes, as I said, atomicity is also important. So how do we do that? We cannot do transactions across two different databases. Two-phase commits or distributed transactions are very hard. Yet there are patterns which allow us again to do some trade-offs between consistency and the simplicity and the error handling. How do you ensure that which one should given priority over the other? If you really want high or strong consistency between these two databases, you need to think about, can you combine that data, or can you create a third service which will own that data, right? So there are different ways of it. The whole saga patterns, like there are 8 kind of sagas which give you that tuning ability, what level of consistency to use, what level of atomicity to use, and what level of error handling or complexity of the error handling itself. Again, as I said, all of these challenges by themselves are a topic of discussion. In the interest of time, we can move ahead. Yeah, and then all of this complexity is actually coming because of scale. We are talking about the volume of data, we are talking about the size and shape of data, we are talking about the millions of users that are being served out of this transactional systems. So how do we ensure we get scalability with the federated system or the modernized system? Earlier it was one part, it was one database, one system, one hardware that was scaling, right? But that hardware was built for that scale. While when we modernize it, when we move to a cloud native world, there are different technologies. All those database boxes that you see there, they themselves may be different data stores, different data technologies, SQL, NoSQL, graph, time series, anything, right? How do you ensure all of them scale, right? Which means there is a complexity involved, there is an additional effort involved there. Plus, in the service or processing layer also, we may either have batch services or real-time or online services or even analytics that has to happen. So, within those services also, scaling for a batch versus scaling for a real time will have completely different trade-offs, right? And within online systems also, a stateless service to be scaled versus a stateful service to be scaled, a completely different challenge. Stateless services by themselves do not need to store anything, so you can, with containers, Kubernetes, you can spin up multiple instances of it. But ultimately it has to talk to data. So the data layer scaling is another challenge. But consider stateful services. In the stateful service also, if you are storing something there, and as your requests or the load increases, your state will also increase, your memory footprint will increase. How do you scale that? So different considerations have to be made for different moving parts, and as the moving parts grow, the complexity of this problem goes. And again, this is for scalability. So quickly looking at each of these technologies, right? How do we scale each of these technologies? First of all, as I said, the data store itself, we have to choose keeping in mind our NFRs, right? Not just the data store, the entire technology stack has to be chosen keeping in mind the NFRs. And keeping scalability as one of our central considerations here. Whether we go ahead with SQL or NoSQL, a very plain thought would tell me that okay, NoSQL is distributed, partitioned, replicated, I can scale, I can throw more hardware at it, and I can increase the number of operations, database operations that I am doing on that database. But there is a catch, there is an eventual consistency. How does it matter? We have seen it working, right? So the topic of consistency itself will probably decide whether you should go ahead with Postgres, any of the SQL databases like Postgres, MySQL or anything, or you should go ahead with NoSQL. And why is consistency so important? Again, going back to the retail example and taking, let's say, one order. I'm placing an order, I'm putting some, let's say I'm paying some money. Whether my payment is successful, but let's say even if the payment is successful, the inventory was not allocated or the inventory was not deducted also, or the vice versa, right? Payment failed, but inventory was changed. In any of these two cases, it is not an acceptable scenario. And consider millions of such orders happening in an hour, right? So which means if something goes wrong, there is a high probability that over a period of, let's say, one day, there are so many errors happening, which means your business model itself is not reliable. It's not a stable system. It's not an accurate system. It's not working to what you need. So, as I said, although we need scale, again there is a trade-off whether we want strong consistency versus scale. And unfortunately, there are technologies that kind of give us a scale with SQL, but those are yet to get to a stage where we can say that, okay, we can definitely take out the existing SQL databases and replace them with the new technologies. Technology is still maturing. Probably 2 years down the line, 5 years down the line, we may be in that state where we may not have to trade off, let's say, scalability for consistency. Yeah. And what does that mean for us now? While we talked about this theoretical choice between the data store, right? SQL, not SQL. In our case, how does it matter? We know we want strong consistency in many of our systems, right? And if you take a percentage, right, that's what we were looking at across the different use cases that we had implemented. How many of the systems really need a strong consistency? There is a high chance that more than 40% systems need strong consistency. Which means if you are talking about, let's say, 100 systems, or even if you are talking about 50 systems, at least for 20 systems you need this strong consistency at that scale. and how can we get that, right? The challenge is mainframe was built for this kind of scale. The scale of mainframe, even its reliability and security is unbeatable if we compare it with the new technologies. But there is a challenge. All of the legacy challenges that we talked about till now also matter, right? And yeah, so even if they are currently being trusted for mission critical workloads, we cannot really trade off between the modernization and this, right? So we have to modernize. We have to look at some modern data store alternative for this. And single RDBMS performance, if you look at it, is no way comparable with it. You cannot get more than, let's say, few thousands of transactions from an RDBMS, if we need strong consistency, of course. And there is a trade-off for RDBMSs between availability and consistency. You just have single master writes. You still do not have multi-master writes with that level of robustness as a technology limitation. With single master writes and having this scale, your availability also is a challenge. Now, if you go for strong consistency, you need to design for availability. We'll come to that as to how do we go into the details of that. Now, we talked about different services, right? Stateful services and stateless services. For stateless services, of course, the processing layer itself can be scaled to whatever number you want. However, with the processing layer changes, the load on the database will increase, and the database associated with that service, we talk about it as architectural quantum, right? The service and its database are part of an architectural quantum. Now, when we want to scale it, both need to scale it. So service is easy, but with database, the problem is it can only, let's say, support few thousands of transactions, let's say 10,000 of transactions or 15,000 of transactions. But if you need, let's say, 100,000 transactions, or if you need 200,000 transactions based on whatever your estimates for your business growth are, how do you really support that? There is no option but to have shards, multiple instances of an RDBMS. Each one will be a single master, doesn't know about the other instances. Unlike any NoSQL database where most of the instances are part of a single cluster and there is a coordination between these distributed nodes that is inherently taken care of by the database system. So here what happens, because you can see those arrows, multiple arrows going from the service layer to the storage layer. The reason for those arrows is the service cannot see it as one database, unlike in NoSQL case. The service has to see it as, let's say, 10 or 20 different database nodes. And whenever a request comes, the service has to decide which request will go where. That complexity lies with the service, right? Now, stateful services, along with the state, persistent state, it also has an in-memory state. That is why we call them as stateful services. We need to pull out that in-memory state in order to be able to scale. But when we pull it out, we need to ensure that the caching mechanism or caching technology that we use should also be a distributed and scalable, horizontally scalable kind of a system. Yeah, we'll go in the interest of time a bit faster. Yeah, and again, scaling any of these, be it a database, be it a service, or be it an event bus, scaling all of these systems requires that we take care of or we understand what is the required throughput and what is the hardware requirement for it, right? CPU limitations, memory limitations, hard disk limitations, you may hit any one of these limitations. A simple example that I can talk about here is, usually with microservices, we go ahead with an event-driven architecture, and in event-driven architecture, usually one purchase may get translated into tens of events within the system. So whatever is your required number of purchases or business transactions, you need to multiply and figure out what are your number of events that need to be happening through it. And many a times we have seen that systems like this event bus, which are very central or critical to the communication between the ecosystem of your microservices, that itself becomes a bottleneck. Reason? It could be disk, it could be network. Those were the two things that we have particularly seen, but CPU and memory are also likely to happen if your message size is large. In our case, message size was large, so it wasn't a problem. But if you look at a generic pattern, you need to understand what number of events per second do you need to support, what is your message size, how much of data volume does it amount to, and how much is the capacity of the network or the drive or the CPU that you are using. That's very critical. Plus we also need to understand what is the level of parallelization. So can your event bus scale? It can if your consumers also can scale. So that level of parallelization your consumers also should be able to leverage. Now when we talk about till now, whatever diagrams we had seen, there we had seen one single component of the whole system. But if you put together all of those components, this is how your architecture looks like. And the challenge here is each of these services that you see there, on each of those services, you have to maintain the data schema, or you have to ensure that your data migrations are done across all those nodes that are connecting to the service. Very complicated problem. I just add one column to my customer table. That column needs to be added to all of these databases, not just one. So any system, when any database change happens, it has to happen because each database is unaware of other databases, right? And now, how do we ensure high availability? We saw that with RDBMSs. It is difficult to have availability. We have traded it off for consistency. So here if we look at it, we can see that we will have to have a replica for each of these nodes. Already we had 20 master nodes and each of them needs to have a replica now. Why? Because we cannot make our system unavailable. That is unacceptable for the business. The business will simply say that in mainframe world it was never unavailable. We want to meet that, right? So this is another layer of complexity. Again, we need to rush, and this was for one system. For all the systems and all the databases, this is what the high availability solution looks like. We have still not gone down into the high availability of our event bus, but that is also another challenge. Quickly looking at two more challenges. If we look at multi-tenancy, SaaS platform, I talked about it, right? None of the businesses want to be just by themselves. They want to be a platform. They want to ensure others can use their platform. Consider hundreds of tenants who are using your platform. And while they do that, you also need to ensure how do you isolate them. You have different approaches. What level of isolation you want depends on how is your scalability traded. You can go with siloed, which is the leftmost model, right? You can go with the siloed model where you say 200 clients, I will have 200 databases. But remember, for each client, because of the load, you may need 10 databases. So 10 into 200, right? So that's the siloed model problem. On the extreme right, you see a pooled problem where you say everything is put together in the same database, all 200 clients put together in the same database goes down, all 200 affected. So those are the kind of trade-offs. Again, as I said, each of these challenges are a topic for a different separate discussion. We'll rush together. Yeah, and you now got high availability with all of this complexity. You now got multi-tenancy also with all of this complexity. But imagine that you are in cloud and the cloud goes down. It is happening nowadays. That is a reality and you need to plan for that. And businesses would simply say it never happened in the mainframe world. We were always available, we never had a downtime. Not even when we were rolling out new changes. So you need to plan for a disaster recovery here. The whole data center goes down. How do you still ensure that your business continues operating? And what you look on the right side with the red service, I've just shown one service because again real estate problem, couldn't show all the 220 services. But if one service is looking like this, the architecture for one service is like this, and the number of services are hundreds, and we need to replicate that in the DR site. Imagine what would be the complexity of this solution. Right? All right, that brings us to the end of the presentation. I would just like to leave you with this thought that the real task of not just software developers but the software architects also is to engineer the illusion of complexity. We just create an illusion, but there is a whole lot of complexity that we need to deal with in order to give that illusion to our clients. And while we talked about all of that and we were dealing with, or we had seen these problems in multiple domains, we realized that recently this year, some thought workers, luminaries in fact, they published a book around some hard parts in software architecture which deal with exactly this kind of problems, the transactional data in the enterprise. While there is a lot of literature on the analytical data and how to deal with that, but for transactional systems architecture and transactional data, a very good and a must read, I would say.